Hello everybody. In this video we'll learn the concept of continuum. Okay. To start with, we'd like to ask one question. Like, suppose we have a container in which we have gas molecules, and in this container we have gas molecules, and we are interested in finding out the pressure of the gas in this container. Okay, now the question is that how we can find the pressure of the gas in this container. Okay, we will be going through various methods and we will see which one is favorable for the engineers. Now we will see how we can find the pressure of a gas using method 1. So in method 1 we will track each molecules and we'll see how many degrees of freedom are associated with them. So if you see, while writing the equation of states of each molecules, then you see that 3 degrees of freedom for translational motion in x direction, in y direction, and in z direction, right? So similarly, 3 degrees of freedom for rotational motion. Okay, so total, if you see, it is 6 degrees of freedom. Now you estimate that in this container the amount of molecule, you can estimate it if you consider it to be having a 1 mole of gas at STP. You can predict, or rather you can approximate the number of molecules is order of Avogadro's number. So the number of equations you need to solve is order of 6n. That is 6 degrees of freedom into number of molecules. So if you can solve those 6n number of equations, then you can physically interpret the system. Okay, so this type of analysis is what we call as molecular dynamics. Okay, but there is a small problem in that. The problem is that it is easy if you are addressing a small system, but if the system is very big, then it is very difficult to address it, because you have number of molecules which will be very huge, and to solve it, it will be very cumbersome. That is, the problem is difficult to address big systems. So this is about the method 1. As we saw previously, that for method 1, that is the method of molecular dynamics, the number of equations, if it is high, that means the computation becomes more cumbersome in case of large system. But now the question is, what is the alternative? And that leads to the method 2. And in this method, instead of going for a single molecules, we usually go in a group of molecules instead of just simulating each molecules, and this group is represented by statistical properties. Okay, and that is quite popularly called, where this type of analysis is done, is kinetic theory of gas. Okay, now you can see, as we are trying to track, instead of tracking each molecules, we are trying to go for the group of molecules, so the computation is quite easier, right? So computation is easier. On the other hand, this type of method is called microscopic approach, right? Now initially what we saw was tracking each molecules and trying to address the system that we do in molecular dynamics. Then we saw another method where instead of tracking each or simulating each molecules, we are considering a group of molecules using statistical description. Okay, and that's what is kinetic theory of gas, and which is a microscopic approach. Now somehow microscopic approach has its own implications, but we have to remember one thing: what we are interested in. We are interested in finding the pressure of the gas, and you know that from a microscopic point of view, the pressure is actually the consequence of the change in momentum, molecular momentum, as it encounters with the wall. Okay, but is it a simple way? Because from an engineering point of view, we are looking for a robust way to find out the pressure. Instead, what we think of some device, and in that device, if you can measure a force that is applied on the wall in a normal direction and the area upon which it is acting, if you can find, then definitely you can find out the pressure in a more convenient way. Okay, so that would be great for us if we can somehow find out the pressure in a more easy and simple way, rather than going into the molecular level, or rather going into some statistical description. So this type of analysis or way is called the macroscopic approach. And in this, somehow, if it works, then we can consider fluid as a continuum medium, disregarding the discontinuity. Now you can see a container containing liquid, and if you do a bit of zooming, you'll see that what you can see water inside this domain. Okay, you zoom it more, you can then see the molecules. So ultimately what we are looking for is not going to this molecular regime where there will be a discontinuity between these two molecules, but rather we will try to analyze in a domain where you cannot see any discontinuity, as if you can treat this medium as a continuous one. That's what we call as macroscopic approach. So as you saw that previously we zoomed in this, and we got a fluid to be continuous one, and we further zoomed it, we saw there is a discontinuity between the molecules. Okay, but this domain that we are working in is actually the macroscopic approach, where we treat fluid as a continuum one. Now the question is that we all know that there are discontinuity in reality, but the question is that when we can treat the fluid as a continuous one, that is something like an hypothesis, and that's what is called as continuum hypothesis. Actually, there is nothing called continuity in the fluid. There will always be a gap, but apparently you can treat the fluid as a continuous one. Now the question is that when it works, what benefit we have? And second question, does continuum works always? Now if this continuum works always, then we can use well known differential calculus to manipulate properties. That means you can have a point-to-point variation of a property within the fluid which is continuous in nature, and you can use differential calculus to manipulate the properties. Now we have understood that if continuum works, we can use well-known differential calculus. Okay, as there is a small spelling mistake, it's benefit. And if it works, we can represent the property as a function of any property as a function of space. Okay, so now we have answered it. If continuum works, what benefit it will bring us. Now we are interested in looking, does continuum works always? And to answer this, we would like to find some important property of a fluid, that is density. Now our objective will be to find the density of the gas. Now we can we define density of gas? So suppose we define density as the mass by volume. Okay, now these molecules, if you typically see, is having each mass, and the number of molecules you consider, if you are trying to find out the density, it will be like n, the number of molecules, into the mass of each molecule divided by the volume over which the molecules are present. Now the question is that what would be that volume? Now you know that there is a container in which a molecule is the gas molecules. You zoom in some portion of it, and now you're interested to find out the density, and for that you selected a small domain, okay, where you're interested to find out the density, and the density is defined as m by v, and that we can say like number of molecules in this into the mass of each molecule. That will give you the total mass, and divided by the volume which is encompassing the molecules. Now the question is that how small or maybe big it should be, so that to get point to point variation. If it is like limit delta v tending to 0, m by v, that's how we define density. Or whatever this volume should be tending to some critical value. That is our big question. Will it be tending to 0, or will it be tending to some critical volume? So as I was talking about it, we have a small volume which is our interest to finding out the density, and you have two molecules, and you know the molecules will be having collision between them, and as it is colliding, you see that after collision this molecules will come out of the domain, and this molecule will come out of the domain. So you can really see that there is uncertainty in the occupancy of the molecules within this domain. Okay, so the error may be close to 50% to 80%. So you can really see that the two molecules after collision, it's coming out of the domain, and it will encounter a type of problem that's maybe close to 50% or 100% for the molecular uncertainty in the position in the domain. So as we saw that in this volume, when these two molecules are colliding with one another, you can see that after collision it is coming out of the domain. That will bring about a very high uncertainty error, right? So the question was when that can happen. Is it when the volume is small, or the volume is not so small but has few number of molecules, like a rarefied system? Okay, so exactly what we want. So the exactly what we want is that, so that after collision this molecule should not come out of it. That means we need small volume with sufficient number of molecules. That means that even after, if suppose it has another two molecules, and when it is colliding with one another after collision, it's when there will be a higher chance that before it is going out of this volume, it will again collide, and in that way it will somehow it will be hindered or prevented from going out of the system. So that means we need a small system with sufficient number of molecules. Now the question is that we mentioned small, we mentioned sufficient. These are all sort of qualitative type of description. So we need to come up with a quantitative way to appreciate through some parameter or by some combinations that will actually involve these two things, so that we can make sure that that volume or the number of molecules is sufficient to measure the density and there will not be any error. Now we will try to address from qualitative description to quantitative description. Suppose you have a system something like this, and you have two molecules, suppose. So you know that one parameter that can guide us the relation to the number of molecules is the mean free path. How? Because mean free path is the average path covered before encountering a collision. Suppose it collides with it, again it has to travel a distance of lambda to collide with another molecule. Okay, and that will give you directly the relation with n, because more number of the molecules, the lambda will decrease. Okay. On the other hand, for the volume, if you see, so volume will be guided by the characteristics length of the system. Okay. So as we were talking about that, for getting a continuous variation of density, one was the number of molecules and another was the volume. That was more important to us. Now n we can relate with the characteristics length, n we can relate with the mean free path, and volume we can relate with the characteristics length. Now what is characteristics length? Suppose you have a flow of fluid in a pipe and you see the variation of velocity is across the radius. So the characteristics length is the distance over which the change can occur. So for a pipe it scales with r, and in engineering practice, instead of r for a pipe, 2r is more relevant, that is the diameter of the pipe. But it doesn't really matter when you are talking about order of magnitude. Only thing which it scales with, that is the radius. Okay. So now, as we already understood, like a case when lambda is greater than l, that means the mean free path, that means the distance traveled by the molecules after collision is greater than the length of the system or the characteristics length of the system. Then we can call it as rarefied system. Okay. On the other hand, if it is lambda is less than L, it is not so rarefied, as before traveling a distance L, it will again collide. So that is what the favorable thing, so that the molecule will not leave the system, and somehow by doing that the uncertainty error will be less. Now we understood that not only lambda is important, but L is also important. So we will define a parameter which is called as the Nusselt number, that is defined as lambda by L, and that will guide us the validity of the continuum hypothesis. That means if lambda by L is small, then it means that the mean free path is much smaller than the characteristics length, and then continuum will hold good. Okay, right? Now for practice, if you typically see lambda by L that is the Knudsen number, I may denote it by Kn. So if it is less than 0.01, we can consider that we can consider the fluid to be continuum, and we can use the well-known differential calculus. And also, as you know about the no-slip boundary condition, because whenever a fluid is flowing in a tube, you know that close to the wall there will be the relative velocity, the tangential direction will be 0, right? So that no-slip boundary condition will hold good within the continuum zone, within the continuum paradigm, where this Knudsen number is much less than 0.01. Now, if this Knudsen number is between it will generally threaten no slip boundary condition. And if it is from to 10, then there is a transition, when there will be a chance of slip boundary condition, more going towards, whenever you go towards the wall, you will see that the fluid will try to slip. That's when we cannot apply the well-known differential calculus, where we cannot represent the property as a continuous function of space. As we considered, if Knudsen number is less than 0.01, we can assume the fluid to be a continuous one, disregarding the discontinuity. Now let us plot density versus the volume that we were really talking about, because at times we thought density to be del V star mn by V, okay, where V tends to del V star. Now we understood that del V star cannot be 0, because we understood there will be some issue with the uncertainty, because if you make it very small, then or maybe tending to 0, the molecule will escape, and that will bring about a uncertainty error as far as the occupancy of the molecule is concerned. Also we understood like that it will be tending to some critical value where you can really appreciate that, and that was guided by Knudsen number, which is basically lambda by L, that is the mean free path and the characteristics length of the system. It not only depends on single lambda, but also depends on L. So if you try to plot density versus del V star, then you will find at the beginning you will have some sort of fluctuation. Moment you increase the volume, at some point this fluctuation will die down, right? And after some time it will again be changed. Okay, there will be some fluctuations. Okay, so now you can demarcate into 3 regions. One where you will get molecular uncertainty, the domain where you can really consider the fluid to be a continuum one, because there is no instability. Okay, and here after this point you are getting what is called as macroscopic uncertainty, that whenever you are trying to increase the volume to a very huge one, then you can really think that there will be also a chance that this density will vary with space. That is what we call as spatial variation. But whole point that we are interested in to work in this domain, where we can use well defined differential calculus. Now, based on measurement and simulation, a little bit of idea that I want to give is like 10 to the power 6 molecules in a volume can give you a stable measurement. Okay, if you think of an air at STP, standard temperature and pressure condition, you'll see that del V star close to 10 to the power minus 9 mmQ, and the molecules of air close to 10 to the power 7, and this will give you a stable measurement. Just to give you an estimate of the size of the del V star and the number of molecules, that will give you a stable measurement. So at the end, we would like to summarize. Now to summarize whatever we have done, the continuum hypothesis, if it holds good, we can apply well-known differential calculus. Okay, as we can represent properties as a function of space. And on the other hand, if we see that we defined a very important number, Knudsen number, sorry for the previous explanations where I mentioned SON, it will be SEN, and that is defined as lambda by L. So for practice, when lambda by L less than 0.01, then we can easily, or rather we can comfortably, we can consider this continuum hypothesis. And in that, for that condition, the no-slip boundary condition will be valid. Thank you.